So I zoomed in on the previous graph. Here's the tangent line, here's the curve. So our goal is to find the slope of this tangent line, and by finding that slope, we would find the slope of the point that the tangent line goes through. But the problem is that we still only have one point. This tangent line was just a random line that we drew on the graph. So we have no idea what the equation of this line is, so picking 2 points on the line, we don't know what this other point is. The only point that we know is from our function that actually intersects with the graph, which we can actually find. This one, we just drew a line. We have no idea what this point is. So we're still basically at square one, but we're still trying to find the slope of this tangent line. We still only have 1 point, so what are we going to do? What we're going to do is actually basically approximate. If we know the points on this curve, right, we define this curve as x squared. We know how to find the y values for every x value. In contrast to this, we have no idea what this equation is. If we pick 2 points on this curve, say my other point is right here. If we pick 2 points on this curve and then take the slope between them, right, we need 2 points for a slope. Our tangent line, we couldn't find the slope because we only have 1 point. So we need 2 points for a slope. I picked 2 points on the curve because we know where those points are. If I pick 2 points on the curve, find the slope between them, and if that slope is decently close to our tangent line slope, like if it looks similar to the slope that we have over there, so I'll connect these two. So I connected them. Now we're able to find the slope of this orange line, this secant line, because we have 2 well-defined points on this curve, and this slope right here, this line, is actually decently close to this one. So if we find the slope of this, we should be close to the slope of this, versus if I picked a point like up here, right, and then drew a line up to there, that slope would be way off. But this slope is pretty close to that. So let's try and find the slope of this line. If I take this point, so this is our tangent line, it goes through the point. Let's call this x-coordinate x, generic x, and then what would this y-coordinate be? This y-coordinate would be f of x. Now if we go over to our second point, let's call this second point the x-coordinate for the second point. Let's define it as just a certain distance away from this x-coordinate. So, right, x is just any number. Let's call this new number over here x plus a certain amount. Let's just call this certain amount right here. So to go from here to here, we went h. So to go from here over to here, this distance right here is h. So our new x value is just x plus h. This x value is x. We went at h plus x. We went h past x. And now our new x value is x plus h. All we did, this is a number, and we added another number to that number to get a new number called x plus h. And this is our new x-coordinate for this point. So if we wanted to find the y-coordinate, now we just find f of whatever. So in this case, it's f of x. Now we have f of x plus h, right? We just take whatever we have for our input and put it into the function. So our curve is f of x. Our x-coordinate is x plus h. So our y-coordinate is f of x plus h. So now we have 2 points, x comma f of x and x plus h comma f of x plus h, right? These are just any numbers and then the function evaluated at those numbers. So now we have 2 points. We can find the slope between the 2 points, and then that slope that we find from these 2 points is going to be decently close to this tangent slope. So if our slope is equal to the change in y over the change in x, delta y over delta x, slope equals, what will we have for this situation? So we went up, our rise was whatever this minus this is. So y2 minus y1, this minus this, f of x plus h minus f of x. So that's what that represents, our delta y divided by our delta x. How far did we go across? Well, we defined it as x. This is our x-coordinate, and this is our second x-coordinate. We defined how far we went across as h. So we could just write h in the bottom, but for the sake of coherence, let's just say x plus h minus x. And these x's would cancel if you did x minus x, and you would just be left with an h. So let's do that real quick. And that is what we get for our slope. So remember, these are just numbers, right? F of x plus h could be like f of 5, and that could be like 7. But what we have here, we just arbitrarily defined it so that we can do more math to it than having a concrete example. So down here we had x minus x, that canceled out. H is now our delta x, which makes sense because we defined this to be h away from this, so the amount that we went between the two was h. But now what I want to do, so this is our slope right here, right? This is our final answer for our slope between these 2 points. But what if I wanted a slope even closer to, even more accurate than this slope to this one? So what if you said, I want to find a line even closer to this tangent line than this secant line currently is. I want to find a slope, so this was our slope that we got for this orange line. I want to find an even more accurate slope than that. Well, if we pick 2 points, that's how we get a slope. So if we keep this point the same, x comma f of x, what point would we pick to get an even closer slope than the one that we currently have? So if we pick a point over here, right, this is going to be much more vertical than this slope. And if we pick a point like way over here, right, this curve goes in this direction, then it would be like negative, so that would be far away. So what we have to do, right, this one was decently close. What if we went closer to our x value and drew a point right over here? So now if we picked a point right here and I connect the two, now this new green line is even more accurate than this orange line is to this black line. So we move this point further to the left along the curve, closer to our x comma f of x. We move this point over here and got a more accurate slope. So what's our new point right here? Well, if we want to use the same convention, what we were essentially doing was shortening this h value. So if h is the distance between the 2 points on the x-axis, these two, this and this point, were more distant than this and this point. So all we did was we shrunk our h. If we call this new one x plus h, just scribble that out. Our new x plus h, we have a smaller h than before, and we have a more accurate slope with that smaller h. So now we have x plus h, and over here we have a new f of x plus h, f of x plus h, scribble that out. And now our slope is even more accurate than it was before. We have the same slope formula though, right? Our rise is still f of x plus h minus f of x, and our run is still h. It's just that the increment between x and x plus h got smaller and our slope got more accurate. Now maybe you can see where we're going with this, but what if you moved your point over here along the curve? What if you moved it further left along the curve, even from this right here? Well, now we would have an even more accurate slope than the previous two that we had before. So all we're doing, right, we're shortening the h. We had a longer h here, a longer distance between x and the other x, and then we shortened it. This was a shorter distance, and now we shortened it even more, right? This now here is a way shorter h. We got an even more accurate slope with that shorter h, and now hopefully you can see the pattern. If we were to shrink this h just means the distance between the two x values of the 2 points, because we have to have 2 points to find a slope. But what if, by approximating between 2 points, by moving this point to the left and to the left and to the left and to the left, and all the way until they're almost on top of each other, but not quite because you can't find the slope at one point. But if we shrunk h, if we shrunk the distance between the 2 points on the x-axis really, 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 really small, like 1 times 10 to the negative 1,000, that small, I think we would have a really accurate estimate of what this tangent line is at this point. And we did this, right? This is just limits. This is the limit as h approaches 0. This is the limit as the distance between the 2 points, right? This right here was a long distance away, shorter, 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 until that distance approaches but never quite reaches 0. So this limit incorporates the fact that we need 2 points to find a slope, but it's saying, what if we make those 2 points so infinitely close to each other that the distance between them is almost 0. Never quite 0, but almost 0. So our formula is still the same, right? We define this pretty arbitrarily, so we still have x comma f of x, that's the line through which our tangent line was drawn. But now we have x plus h, where h is infinitely small, so the second point next to it is infinitely close to x, and we saw that as these points got closer and closer to the point in question, the slopes got closer and closer and more accurate to the tangent slope. And the whole point of this exercise was to find the tangent slope, and that's what we did. We found the limit as x approaches h of f of x plus h, that's just the y coordinate of the second point, minus f of x, that's the y coordinate of the first point. So this is the rise, the delta y, over the run, which is h, which now we know is infinitely small, approaching zero, right? The distance between the points is approaching zero, and our slope is approaching the slope of that tangent line. Our slope was here, it was way off, closer, closer, infinitely close. It should be exactly the same as the slope of our tangent line. So that is where the definition of a derivative comes from. And now when you have actual functions, like we had an x squared up here, you can apply this formula to x squared or any function and find what the limit is as h approaches zero, and that is the definition of that function's derivative.